Hello everybody. We are now moving on to chapter 2 in our book, and in this chapter we're going to start to kind of ramp up our Python skills a little bit. Chapter 1 really kind of introduced you to the whole concept of programming, kind of reiterated the whole problem solving approach. It showed you how to do print statements to get stuff up on the screen, how to work with the tools a little bit, how to save your files, how to run things, and kind of just get you into that workflow. What we're going to learn in this chapter are what I would consider more the formal aspects of learning a programming language, the little bits and pieces that we need to understand on how programming works. And they talk here about these different topics, and some of them are the fact that we're going to be working with numbers, we're going to be working with strings as we have already. But more importantly, we're going to learn how to take those things and apply them to variables, which I think is pretty important. So these are the chapter goals. So we're going to learn how to work with variables and constants, what those even mean, the different types of numbers supported by Python, how to do commenting, how we do this thing called an assignment statement, which looks like math but isn't, and then how to actually do math. Those are both pretty important. We're also going to look at programs that read and process inputs. So in other words, either bringing information in from an outside file or asking your user for information and then using that to run your program. How to work with strings on a little bit higher level, and then a little bit of an introduction to working with graphics programming, which I think is cool so early in a programming book. All right, so those are the topics, and then these are the chapter sections that correspond. So the first part of this is going to be working with variables. Now the way that I like to think about variables, and I know that it says a whole bunch of stuff here on the screen, and you know, different textbooks will kind of teach you in different manners. But the way that I think of a variable in a computer program is this. When you create a variable, you're basically creating a location in the computer's memory that you're giving a name and you're putting stuff into it. I always use the analogy of like a box, okay? And I think of like a cardboard box, right? And I have it sitting there. And I can put stuff inside that box to store it. And I can take stuff out. I can actually put stuff in there and I can add stuff to it, or I can just remove some of the stuff. It doesn't have to be all or none. And then certain boxes will hold certain types of information. In other languages, so some of you are concurrently taking Java with this class. If you're like a full-time student, you're also learning Java programming. And in Java programming, when you learn about variables, you start to learn that you have to tell it what kind of box it is or what kind of variable it is. So if you're putting an integer in there, a number, counting number, you can't put words in there. And guess what? Python doesn't work quite that way. Java is what we call a strongly typed language where you have to strictly follow the rules. Python is a lot more forgiving. It's like JavaScript. I can put text into a box. I can then put words into a box. It's not recommended, but you can do it. So if you use that analogy, that I think really helps a lot. It's also possible to actually create the variable and not put anything in it. The moment they put something inside of a variable is when we initialize it. So that's what the next few slides are about. All right. So notice here, it says you define a variable by telling the computer what name you will use to refer to it, and then also what value you're putting inside. In Python, if you don't give it a value, it kind of really doesn't exist yet. In a language like Java, you can actually create it first and not put anything in it. And then the value inside of it is called null, nothing. It's actually the absence of anything, which is not even nothing technically. But all right, let's take a look at this little graphic here, and let's see how we actually do the assigning. So take a look at the information. Notice that we have a keyword, all right? And the keyword is total. And it's not a word that's used by the language itself. So for example, I couldn't create a variable called print because print is reserved by the language to put stuff on the screen. So I could choose any other word aside from print, for example. And there are certain words that are reserved, and those are listed in the back of your book, actually. And you get to know them over time. And then if you pick it by mistake, the debugger will tell you, hey, you can't use that one. That's a reserved word. Pick something else. Okay. So in this case, they chose the word total. Then they have an equal sign, and they have what there? 0. So what that means is total is the box. We just created a box. And then equal says whatever is on the right side of the equal sign, we're putting inside the box, or inside total. That's what that means. And one thing that you should not mistake here is that an equal sign does not signify what it does in math. In math, you go 1 plus 1 equals 2, right? And the equal says that you're doing math and you're getting an answer. In programming, the equal sign says that you're assigning a value to a variable. Okay, and that's a really important distinction.
So you can reassign a variable sequentially anytime you want, and if the IDE throws an error, then the IDE is retarded.
That hypothetically, yes.
Okay.
That's an interesting commentary, Tom. Yeah, it could be. Not all IDEs are created equal. Let's just put it that way.
I'm well aware of that.
Okay. Now, the next statement here, where they are using words instead, and I'm going to zoom in a little bit. Notice that they say total equals bottles times bottle volume. Okay, so let me explain what's going on there. Once you've created a variable and you put a value inside of it, you can now use the name of the variable instead of the number you put inside in place of it. So somewhere else, if you were to use a statement like this, somewhere else in the program up above, we gave a value to bottles and we gave a value to bottle volume. Okay, and then you can just use those like that. And notice that in between them, there's a little asterisk, and what that actually represents in programming is multiplication. You guys might already know that. You can actually also use the assignment of the variable itself on the opposite side of the equal sign. Now, I'm wondering if this is what's going on with you, Tom. The problem with Python is this, is that you have to pre-initialize the variable before you can call it in the same statement.
Right, so if I pre-initialized it on a global scale, then I wouldn't have that problem within a function or anywhere else throughout.
All right. Now the author goes through and he does point out that, you know, there's the equal sign in there. So let me just demonstrate a little bit here, and I think this will probably help you more to see it in action than, you know, like a description in a book. So one thing I'm going to do is I'm just going to kind of copy their example. I'm going to say total equals 0. And then I'm going to print total. Now notice, I could just print the 0, but I'm storing the value 0 inside of total, and I'm just going to run it. And you'll see that it'll output, yeah, see, what is it asking me to do? Save your work first. And you know what, this is chapter 2 now, right? So I'm going to go up a folder, create chapter 2, go in there, and I'm just going to say example. Okay. Now I'm going to go ahead and run it. And it actually already did it. So it just output 0, obviously. So let me demonstrate the kind of thing that we can do here. Now we know that total is 0. I can now come in here and say total equals 1. And, you know, maybe the better way to do it is like this. So total equals 0. We print it. And then we make it equal 1, and we print it again. So I'm just going to run that. Save my work and hit run. So it outputs 0 first and then 1 because the value was changed to 1 after I printed it. You see that? If I remove this print statement, what's it going to output? 1, right? I set it to 0, and then I set it to 1, and then I print. So it's going to print what the last value of it is. Yes, Alex?
Can we try that, but with the, on exercise 1?
What Alex is asking me to do is, like, when we were working on the chapter 1 exercise and we couldn't, like, put all this stuff into the same space, could we, you know, like, throw the variable in and actually make it work? Yeah, you know what? We totally can do that. So let's show how we could. So what I might do is I could say total equals all of this, all these numbers here. And then I'm going to cut that and place it here. Is that an okay statement? It sure is. And then I can say print the sum of the first 10, the sum of the first 10 positive integers is, then I would do the plus sign, and then I would do total. Will that work? It's not flagging it, right? So it must work. Let's try it and go ahead and do a print. Yeah, we still have a type mismatch. So what needs to happen here is it needs to be converted to what? A string. And there's actually a method for doing that. This is coming up soon, though. All right. But this is demonstrating the next step up. So I still kind of am stuck doing this approach for now, which is print total and now it'll still do it. But it does demonstrate that you can do some math as well, store it, and then output it. Once we learn the little trick for converting it to a string, that will unlock the door. Okay. But I don't want to jump quite there yet. But that's a good logical place to go. All right. So he continues this discussion of the assignment statement, and they talk about some examples. And I'm not going to necessarily work through this example, but I do want to talk about it really briefly. So they have this example in the book, and I would hope in the book that you guys take a moment to kind of like leaf through it. It says, soft drinks are sold in cans and bottles. The store offers a 6-pack of 12-ounce cans for the same price as a 2-liter bottle. Which should you buy? Which is a better value? Well, for me, it's a no-brainer. I just buy the 6-pack because I like my soda to stay fizzy. I mean, that's just, so I would just throw the 2-liter off the table. All right, but what they're trying to tell you is, like, which is a better value? Okay, so a 2-liter bottle has, 2 liters in it. But a 12-ounce can, so this is a conversion, is 0.355 liters. So what they want you to do is to do the math. Okay, so here's what they do with the math. They will, and this is where I think I have some solution files for this. So I'm going to just pull it up and show it to you. Pause the video for a sec. All right, let's talk about the type of things that we can actually put into variables in terms of numbers in Python. Python essentially lets us work with 2 different number types, and that would be integers and what we call floats. And they really simplified it really to those 2 number types because they figured out a way with this language to really kind of cover all the different numbers that you might need using those 2 approaches. Other languages do have very incremental data types for numbers, although it's important to note that integers and floating point numbers of some sort are included in every language, although they can be called different things. The integer data type is pretty common. Just remember, in Python, we don't actually need to formally declare it, we just use it. So if you want to just declare something as an integer, you just simply use a whole number with no decimal points after it. Simple as that. If you want to declare it as a floating point number or a fractional number, if you will, it has to be in the form of a decimal, and you have to include the decimal point. So if I wanted, for example, this is a little bit of a talk we were having here about if I wanted to cast the value, or in other words, imply that it's a floating point number even though it's a whole value. So I would, let's say if for number 2 it was 8, but I still want it to be a floating point, I would say 8.0. And that will treat the number a little bit differently, and it also results in different math results when you multiply and divide. So that's why that's important. The other data type that we'll typically use is what we call a string, and we've done that right from the beginning, and that's where you put characters inside of double quotes. If you put numbers inside of double quotes, those also become characters, and then you can't do math with them. All right, that's a pretty simple little thing. Once you actually have values inside of a variable that's declared, you can change the value. All you have to do is issue another statement indicating how that value is changing. Sometimes you do like what's shown on the screen here, you just hard code it. You just, brute force give it a different value. More often though, what happens in programming is that value on the right hand side of the equal sign is programmatically controlled. In other words, something happens in the program that allows the value to change. It could be something as simple as this. When you start out a program, you might set something to a value of 0, and then you ask your user from the screen, you say, what is your age? And then you type in a number, they press enter, and then that value changes based on user input. So that's pretty common. So take a look here at this next little thing where we're actually going to change the value by doing some math, including the variable that we already have. So keeping this slide up here in mind, we started at cans per pack was at 6, right? So there's 6 in there. But we're going to add 2 cans. What are we adding it to? Are we adding it to 6? We are. But what if we don't know that right now? We know that cans per pack was preset to 6. Now we're going to add 2 to it. It does that math first. So it reads what it was, which was 6, adds 2 to it, becomes 8, and then whatever's on the right side gets stored on the left side. So whatever is on the right side of the equal sign gets placed in here. And if you're coming in to math like this, you got to keep in mind that we already had it set to 6. That's why it was happening. Okay? So that math is calculated, it turns into the number 8, and then it gets added back. Now, cans per pack here left off at 8, so then if we do it again, cans per pack, which was 8, plus 2 now becomes 10, and that goes in here, and then cans per pack becomes 10. So if we do it again, what does it become? 12. If we do it after that, it becomes 14. See the pattern? Okay. All right, they do give you this little warning, and this goes right in line with what we were talking about. If you know you're going to do math with a floating point number to determine like a tax rate, even if your tax rate happens to be 5%, you should probably enter it as 5.0 so that it calculates out correctly when you're dealing with decimal numbers that are multiplying against it. That comes from a little bit of practice. Like this is not something you would normally intuitively know, but one of the little tips I can give you is whenever you do math in a program, it's not a bad idea to go to like a calculator or a spreadsheet or even pencil and paper and verify the math that you're doing and the answer that you expect to make sure your program is set up correctly. Once you understand how the programming language handles those numbers and values, then you can work with it more intuitively. But until you figure that out, it becomes a little bit of a challenge. All right. So the author here is asking us to create this program. Now I'm going to go ahead and do this. And frankly, if you guys have the PowerPoint open on your screen, you can copy this text and paste it into a file just like I'm about to do, just to try it out. Okay? So he's asking us to create a program that does all this. So let me copy it all in. I'm just going to copy this part of the code, and then I'm going to go back to Spyder, and I'm just going to keep working in my example document just for the sake of it. In fact, I'm going to just delete all the junk in there and just paste this in. All right. And remember, he's got a goal here, that we're testing different types in the same variable. So first, we are going to start out by making tax rate. It's a variable we're declaring. So we just say tax rate equals 5. And notice he's got a little comment after it that says that's an integer. So we'll do that. It'll print out a 5. Then we can take that same one and turn it into a float and output it. And then we can turn it into a string and output it. Now after the last one, he'll take that string and add 5 to it, and we'll see what the output is. So let's go ahead and actually save this and run it and take a look at the output. And then, oh my God, we got all sorts of problems here. You notice that? And I'm going to expand the screen because there's more than one problem. So it started out just fine. It gave us 5, right? Then it only output 5 the second time. That's not what I expected. And then it output non-taxable, and then it broke, right? And what it said is there's some sort of an issue here. It says you can't do that. This is the same message that we were getting before, right? We already figured out how to fix that one, right? And this author does what a lot of authors do, is you run it, and then you find the problems, and then you have to fix it. All right. So what was the problem with what we did here? Let me do this. Was any of this problematic? I'm going to say it was. I'm just going to run that little bit of it. You know what it is? It output the 5 because we put 5 in it. But then when we tried to put 5.5 in it, it still gave us 5. And David, you just chatted something over. I didn't see what it was. So can anybody give me an answer? Why is this happening? Yeah. Okay. So the error that's happening here. This is really kind of silly, right? You got to look at the details. Here we're printing tax rate, right? And when we define tax rate, notice how it's spelled. This is like kind of a harsh way to learn this lesson, really. It's all lowercase except for.
The second one has a capital R instead of lowercase.
Yeah. So here when we said tax rate, notice it's a lowercase r, but we were still printing the first one. So if I do this and run it, now they both print just fine. Another. Can you please mute your mic? Thank you. It was really loud in here. All right, so there's a couple different things we can do to fix this. We can also do this. Can I leave that alone and actually change this R to a capital? And then run it. Yeah, that works too. All right. I'm going to Control Z that though. And we did that. And then I had removed the other stuff and I'm going to drop it back in. Is there any problem here? We already know why this one won't work because we figured out that issue. So let's deal with this. Now I have 3 of them, right? What's this going to output? 5, 5.5, and non-taxable, right? Should. Let's run it. See? Yeah, it does work. The thing that's kind of fascinating here, folks, this one's printing out right now because now what's inside the parentheses is matching the variable name. The other thing I want to show you, and this is pretty important, because you can't do this with most languages. You can do it with Python, you can do it with JavaScript, because they're both what we call interpreted languages and not strongly typed languages, right? So here I'm going to go from an integer to a float to a string, all with the same variable, printing out each one along the way, and it will work just fine. It allows you to do that. However, really strong word of caution, try not to do that. If you're going to start with one data type, stick with it. I have seen people creatively use that to their advantage, but I think it tends to cause more problems than solutions. That last line that we removed wants us to put in tax rate plus 5. Will that work now? It won't work in that spot. Why won't it work in that spot? Because when we do tax rate here, right, we switch to a string, and all of a sudden we're trying to add 5 to it. Right? That won't work. In fact, let's just run it and I'll prove it to you, right? Throws all sorts of stuff out there. You know, you see that, like, you know, blah, 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 type error. Okay, that's not good. But what if I took that line, just this line, and put it here? Will that work?
Would it not work since that additional 5 is not stated as a float?
Yeah, that's kind of like the thinking, right? So you got one, at this point, tax rate is 5.5. It's a floating point, and now we're going to print it out, and then we're going to print it out plus 5. So will it do the math or will it not? That's really the question. All right, so let's save it. You know what? Let's try it and see what it does. It does do the math. It's okay doing the math because, you know, a floating point and an integer, I mean, yeah, they're different technically, but they can still be added together. I can't really add a number to words. Okay, so these are the kind of little nuancy kind of things that you figure out with numbers and strings. And this is kind of a nice little example. Maybe a little long-winded, honestly, but all right. Let's move on to this next thing. So in all programming languages, whenever we actually use a number or whenever we actually use text, we call those literals. Okay? So if I type a variable name and assign it a number value, that's called a number literal. Okay, so here's examples of them. And then it shows you what the data types are. And this table's in your book too. So if I look at the number 6, or a -6, or a 0, they're all integers. They're single counting numbers. There's no decimal point after it. There's no fraction after it. No exponents or anything like that. They're all integers. Any positive or negative counting number. A floating point number can be something that might be a fraction. So I can't do fractions in programming languages. I can't say 1/2. Can't do that. I can divide 1 by 2 and come up with 0.5 though, because that's the same as 1/2, right? I can also say the number 1, But if I want it to be floating point and to do floating point math, I have to say 1.0. I can also use numbers that are bigger. So one example is they have numbers with exponents. So just to remind you of what an exponent is, it's when you take whatever number you have times 10 to a power, which just adds a certain number of places to it. So 1e6 stands for 1 times 10 to the 6th power, which is the same as, what is that, 100, 6 zeros after it, 1 million. So 1e6 is another way to say 1 million. Conversely, the next one down, you can do negative exponents, and with negative exponents, you're multiplying by 10 to the negative power, which has you go on the other side of the decimal point. So instead of adding zeros, I think of it like this. Instead of adding zeros, you're adding stuff after the decimal point. So you're adding zeros this way and pushing it back. And the reason we have scientific notation, keep this in mind, is it's a more efficient way to represent really large or really small numbers instead of just typing them in directly. The question you probably should ask is, can I still type them in directly? And the answer to that is, of course you can. But scientists would tend to go with the notation as opposed to writing it all out, especially when it gets past a certain point. I mean, when you get to 20 zeros or something like that, I mean, functionally your brain can't really comprehend it anyhow, so you may as well go with the exponential notation. So that's the notation that's used inside of Python. Other languages have other approaches to do this. In fact, other languages will pull in entire math libraries to make it happen. That's not the approach here. Python does have libraries available to it. We'll talk about those later. Some things that you cannot do, though. You cannot put in numbers with commas in there, right? So if you wrote $100,000, you might write it out in a document and you'd put the comma in there because that's how you were taught. Because in text it looks fine. You also can't type in fractions like the ones shown there. Those will generate errors and it'll be a problem. When it comes time to name your variables, there are certain things that you have to do. So every language has rules regarding this, but there's also something that we call conventions, which are just things that programmers do more as a courtesy than as a rule. Okay? So let's talk about the ones that are absolute rules that you must do. All right? So first thing that is really important, in Python and in most modern languages, there's been this move towards using very verbose names for variables that describe what the variable actually is. So for example, that first bullet, it says, the variable name should describe the purpose of the variable. So can volume, if we're looking at the volume of the can, is a good name. CV, not so good. Because if Joe came in and looked at Alex's code after the fact and called, and it's like, what the heck is CV, right? It means nothing. So use names that mean something. Also notice that when they're naming variables with kind of like two logical words in it, they're not putting any spaces in it. Spaces are not allowed. And then when we get to the second logical word, we use a capital letter so we know where that second word begins. That approach, when you start with a small letter, and then all the subsequent words have a capital letter to start, that's called camel casing. And in the book they have a little picture of a camel. So if you ever hear that terminology, camel casing, that's where it comes from. All right, in terms of the rules that we must follow, and I notice that the bullet points on this slide are really goofy, aren't they? Okay, just disclaimer, I didn't make this PowerPoint slide, so that's not me. All right, so it says the variable names must start with a letter or an underscore. So you can start a variable name with a letter or an underscore, but not what? Can't start it with a number. That's true in most languages. All right, continue with letters, upper or lower case, digits or underscores. So I can use numbers in the variable name, but just not in the first character. So what's not unusual is, let's say I have two different totals I'm keeping track of, I could name one total 1 and total 2. That's fine. I just can't say 1 total, 2 total with numbers. It has to be words. You cannot use symbols other than the underscore. So you can't use question marks, percent signs, and dollar signs. A lot of languages do allow for dollar signs because it connects to other languages like PHP, for example. So you got to watch that one. This is not one that allows for that. I think in JavaScript, and anybody that's had that class can maybe confirm for me, that they do allow dollar signs as the first character, and that is for the tie-in to PHP. All right, and then they talk about the camel case thing, like what they have in the example there. We already talked about that. And then you also cannot use the reserved words that are listed in apparently Appendix C. I'm just kind of flipping my book to that right now. And if you find that in your book, it's like way in the back. And it shows you all the reserved words for Python. And the one example the only really one that we've seen so far is print. So I couldn't call a variable print. If you do pick one by mistake, it will tell you you picked it by mistake. Choose something else. Bad choice. All right, moving on. All right. So just as in the form of a table here, show can volumes, right? Sometimes we get a lot of people that do name their variables with like single letters like this to represent like the same kind of stuff we might do in a math formula. So yeah, you can use X and Y. That's perfectly valid. Now notice that can volume starts with a capital C and there's a warning next to it, right? It doesn't say error, it says warning. Now, it's a convention to use camel casing. That means to start with a lowercase letter. And this gets confused because we do have people that work like in a Microsoft-centric world in coding, where it's kind of considered okay to start with a capital letter. And honestly, it won't break a thing if you do this. It's just not considered normal. And there's another issue that we have as well with variables, and that's when we get to constants. And constants are all named with uppercase. So we tend to try to avoid naming variables with uppercase letters to start with. Start with lowercase. If you have logical words, add that capital letter in the middle. Then they give you all the ones that don't work. So you can't do six-pack starting with a 6. That's a number. You can't have anything with a space. You can't use a word that's reserved by the language. The word class is reserved by the language. And you can't do like this complicated stuff where you have weird special symbols and periods. So the slash is no good here, the period's no good here, and you can't start with a number. It's like 3 strikes, you're out, basically, on that one. All right, so they gave us these tips before. Now let's talk about constants. All right. I mentioned this before. In Python, we really don't have a formal way to force something to be a constant. You just kind of do it by convention. So when we name something all uppercase, and then the convention, this is one that glides across all languages, folks, is that you uppercase the whole thing, logical words are separated by an underscore. And that way, anybody looking at your code can instantly go, oh, that's a constant, right? Now the truth is in Python, that's not enforced. I could assign a different value to bottle volume, and it would work. Why? Because Python allows it. In Java, if I were to declare, let's say, an integer that was a constant, I would actually use the little keyword for constant and integer, and then it could not be changed. That's not possible in this language. However, from a programmer's perspective, it still makes sense to have some things that behave as constants, even though it's not really kind of a thing. That's just a convention you should know. And it carries from language to language with that, which I think is pretty helpful. Here's some examples, right? So we just assume that the first 2 are constants just because of being all uppercase, and the bottom one is not. All right, moving on to another topic here, and that's comments. Now we've been kind of doing this right from the get-go, but comments are basically placed into programs to allow us as programmers to put little notes in the program. Sometimes what I do when I'm coding, especially if I'm working on like a book exercise, sometimes I'll go to the book and I'll copy the problem description from the book and drop it right into my program as a comment. And I'm just gonna like demonstrate. So like we were working on those exercises before, I might like just come in here and grab it, do a copy, go back over to Spider, and let's just say this is a brand new program. I would paste it in. Of course, that's not going to work. But I would put in a comment mark, and I might even separate it over several lines, honestly. I might do something like this, right? And every time you put that hash mark in front of the line, it makes it a comment. And then when I'm programming, the reason I do that, here's the explanation. That way I don't have to keep going back to the book. It's right there where I'm working. So if it says, you know, create this variable, calculate the value, get user input, whatever those steps are, I'll just put them in my program as comments, and then I convert it to code. Then I don't have to bounce back and forth between the book. The other reason that we use comments is kind of like what we demonstrated before, is to just put in little notes. So like if I'm, you know, testing different types in the same variable, I know what I'm doing. Or I might just put in something that says, this variable stores the current tax rate, right? And then I would say tax rate, because that's probably going to be a constant, is 5.6%. Or, you know, if it's a tax rate, actually, how would I probably list it? I'd probably go like this, right? Because that's really 5.6%. Right. Another thing that's kind of interesting is you can have code on the page, and at the end of the line, put it in the pound sign and add another comment, like that. The thing you have to remember about comments is they don't end up affecting your program. They're notes for the programmer. I know that a lot of teachers here, I'm not one of those, and I think I explained that already. Sometimes they'll ask you to put your name in the document, maybe even which exercise it is, exercise 5, the date, the name of the file. So those instructors might get really persnickety about that. I tend not to be. But I'll tell you what, I've discovered over time that when I've coded things and then I had to go back years later and look at it, and you don't remember why you did what you did, and you put no comments in there, it's like shame on you, right? It's your own fault. But if you put comments in there, for as silly as they might seem, they might be so invaluable when you come back later to fix it, you would be surprised how useful that is. Another thing that I do with comments, and this is just a preference now, all right? And a lot of people don't do this, but a lot of things that I do with comments is sometimes I'll try different things, and some things work and some things don't. Most people, when they do things that don't work, they delete them. I tend to comment them out and leave them. And that way I can go back and look at all the things I tried, or how I might fix the thing that didn't work before. And it's already there. Now granted, adding all those lines of codes, does make the file bigger, but there's trade-offs. So you can use those as you kind of see fit. I'm not really huge on forcing people to comment. And there are a couple different styles for doing this. So there are the approaches where whenever the line starts with that hash mark or the pound sign, it's effectively ignored. If it's at the end of the line, it's effectively ignored. There was a different commenting style that they demonstrated in the book that's a little different. Does anybody remember what that one is? In fact, the Spider IDE kind of does it automatically when you create a new document. What are they doing? Because this obviously is a comment, right? So how are they doing it? With the quotes. And it's more like a CSS style thing where you're indicating where it starts and where it ends, and everything in between is a comment. Now, I'm not like a long-time Python programmer. I'm kind of new to it. So I would probably stick with the first approach. Athena, question? Why 3 quotes? Because that indicates that it's the start of a comment. And then 3 more quotes indicates it's the end of the comment. That's just one of the techniques. That's just what they decided to do. You know, whoever created it, that's what they decided to do. Me, I've never seen that commenting style before in any other language, so I would probably stick with the first approach. And I think, you know, maybe in this language this also has a special meaning. That could be. So, just something I want to point out. All right. I want to show you this so that I can explain what are the concepts we've already kind of been hashing through. And that is the concept that in order to be able to use the value inside of a variable, you first need to declare it sequentially before you can use it. So this first example here, oops, I didn't mean to do that. The first example, this statement, the first statement would not work because in order for it to work, it assumes that liter per ounce is already defined. If you switch the order and it's already defined, then this math will work. It's as simple as that. All right, now we're getting to the point where we're going to talk about how you do math in the language. So the beauty of what we just learned, and I just kind of want to reinforce what you just learned. You learned how to do variables and how to name them, right? And what kind of stuff you can put inside them. That's really kind of the crux of it. The 3 data types we can put inside are what? Integer, float, and strings, right? Whole numbers, fractional numbers, words. Now we are going to move forward into doing math, and this is a big part of what programming is, folks. Not that you have to be a mathematician, but a lot of the stuff that processes in the background of a computer program often is done through math, either by comparing things or doing that, you know, adding, subtracting, multiplying, dividing, or just comparing values to see if something is true and false. In this programming language, like many others, the 4 basic math operations are represented by these signs. So the plus sign, the minus sign, the asterisk for multiplication. So if you're new to programming, that might be new to you because you might be used to an X, right? But it's the asterisk for multiplication. And then the forward slash, where your question mark key is, not the one above your enter key. That's a backslash. Forward slash leans, you know, the top of it leans forward. A backslash is the other way, right? The forward slash does division. So they do a little bit of a comparison here, where if you are used to doing algebraic notation, like on the left, a plus b over 2, right, which means a plus b divided by 2, in Python you would express it as follows. And notice the use of the parentheses. So we wrap the a and the b in a parenthesis so we make sure that math is done first, and then we divide it by 2. All right. Now the reason we do that is there's this thing called an order of operations. And there's this thing that a lot of people learn when they're in school called PEMDAS, right? And what's like your favorite way of doing that one? Please excuse my dear Aunt Sally, right? Some people say that. Anybody, just to remember it? But the whole point is you start with your parentheses, then you do your exponents or square roots, then you multiply or divide, and then you add and subtract. So in this, if I hadn't put parentheses around a and b, it first would have divided b by 2 because that would have been together, and then added the a. That's the why. If you're not sure, I always tell people, throw in more parentheses than you think are necessary, and that usually solves a lot of problems. It also helps that if you check your math outside of what you're doing to make sure that it resolves correctly. Takes a little bit of practice at first, but it's not really too difficult. Really same rules as math, but programming will force you basically to remember those rules. All right. Now it's going to talk about mixing number types. And since we have integers, whole numbers, and floating point numbers, notice the simple little equation they're doing here. You have 7 plus 4, basically, that's what it is, which is 11. But because I made the 4 a floating point number by putting 0.0 after it, the answer actually comes out as 11.0. This is a thing we call casting. So the fact that we're mixing the two types forces us basically to cast the value to whatever the greater type is. In this case, the fractional value of 11. It happens with multiplication, addition, subtraction, all the basic operations will do that. All right. I don't want to freak you out, but here's some math that's a little bit more complex looking, right? And I know how it is. I had to take a lot of pretty heavy math, being a computer science major and, doing graduate degrees and stuff. You should never let math intimidate you because it's just a way of saying something. But what they're trying to show you here is how you convert from what is a typical mathematical formula that you might see in like a math book and convert that into something Python can understand. And frankly, this is a lot of what programmers do is they get these kind of formulas and they just are trying to get it into the computer program to do the number crunching. Doesn't mean you have to necessarily understand how the formula works, but you do have to understand how to convert it into a format that the language can read. So what they're showing you here is how we do all the little tidbits. So b multiplied by this whole equation, right? So bx becomes b star. That's pretty easy. Then we got all this stuff inside the parentheses. And really, r over 100 is kind of a separate thing. It's r divided by 100 added to 1. That we can actually all put in one statement because divide will happen before plus anyhow. So I can just say 1 plus r divided by 100. R will divide by 100 first, then add 1. The tricky part comes in to do a power. How do I raise to a power? And Python is a little unique here. In some languages, you just cannot do this. You have to actually bring in math libraries that call in an exponent. Python allows you to use 2 asterisks to indicate that you're raising to a power. That's actually kind of cool and powerful because I don't have to call any libraries in to do it. So in order to raise it to the nth power, we just go star star n. So this equation here turns into this inside of Python. But do notice that b still multiplies against all of this raised to the power, so that's why there's a second set of parentheses around it. Okay? Once again, I'm not going to say, take this math formula and convert it to whatever. I'm not going to do that to you guys on the test. I don't care. I'm going to assume that most of the time when you're working with, let's say, like a scientist or an engineer or something, and they need you to write a computer program and make it do something, they'll help you get it there, right? Or they'll give you the formula to start with. And most of the homework is going to do exactly that. There are some higher end exercise problems I've been noticing at the end of the chapters that I'm like, oh wow, this is enough to freak people out. Don't freak out because I'm probably not going to assign those to you. I'm going to give you stuff that you guys can handle. But I just want to show you that it can be done. All right. There's a different type of division here that you're going to be introduced to as well. So, for example, if I were to take just a regular calculator program, right, or physical little calculator, and you pull it out and you start to do some of these math. So here they're doing 7 divided by 4. So if I divide 7 divide by 4 equals 1.75. Now notice, that we're starting with two numbers that are whole numbers. So the calculator knows what to do. It realizes that 4 doesn't go into 7 evenly and we have something left over, right? So it gives us the 0.75. There's also a thing here, so if in Python, if we do that, that's what the result's going to be. But there's also this thing called floor division, and this is kind of a weird one. So we use two division signs, and instead of looking for the exact answer, we're not looking for the exact answer. All we're really doing is, how many times does 4 go into 7 completely? Once. You can't get it twice, because it's not 8. If it was 8, and I did 8//4, the response would be 2. The floor division, as they're calling it, some languages call this integer division, will just give you the whole number. Now, you might ask, why is that useful? There are a lot of circumstances why that's useful. So, for example, if I was to make change, right? How many quarters can I get out of $1? 4. How many quarters are in 98 cents? Well, 3. Right? I can't get any more quarters in there. There's stuff left over, I know that, but how many quarters can I get in 3? And honestly, this like weird math, weird division, in the next slide we're about to see the remainder division. Those resulted from people trying to figure out exactly that scenario. How do I make change? That's what prompted all this. All right. There's also what we call remainder division, and in a lot of languages call it like modulus division or mod. So if you ever hear, mod, and then the symbol we use to do that is the percent sign. Opposite of what the floor division does, this tells you what's left over. So, how do I make change for $1, right? How many quarters go into 98 cents? 3. For math like this, I want to know what the remainder is so I can figure out what other coins I can use to make that. That's where remainder math comes in. So if I do 7 mod 4, 4 goes in there once, I got 3 left over. It's looking for the remainder. That's why we call it remainder division or modulus. All right? They give an example here. I'm not really, I guess, too worried about that, but the classic examples always revolve around money, and usually what they do to figure out how to make change for something or how to divide up the dollars and cents is by doing a combination of integer or floor division with modulus. So here they start out with 729 pennies, right? They divide the pennies, floor division, the 2 slashes by 100. That tells you how many dollars, right? Then you take the pennies and mod by 100 again. Why? Because there's 100 pennies in the dollar, and you try to figure out what's left over. So what's left over? Now you could totally run this program if you want. It's not really a big deal. And you can figure out exactly what you have in terms of dollars and cents. I mean, you should be able to look at it and say $17.29 anyhow. I mean, you should be that clever. But how do you tell a computer program how to do that? I can look at 729 pennies and just say it's $17.29. I just move the decimal point, right? But if you're like trying to like actually calculate this out, think of like when you guys walk into a store. Now all the stores, like how often do like the cashiers actually like, pull the coins out of the drawer for you? They just have a machine do it, right? What math do you think is happening to make that machine give you the right coins? This is the math. Now they have dollars and cents here, but they also break it down into nickels, dimes, and quarters. So they divide by 25, they divide by 10, and they divide by 5 as well. So that's how they do it. They have some examples here, and I know we're running out of time. I'm being mindful of that, of the math. And I think this is pretty helpful to kind of wrap your head around it. You may see a couple of like simple little questions like this pop up on a test or a quiz, I'm just pointing it out, on how to do basic floor division and basic remainder division or modulus. All right, so if you look at this first one, notice that n is a variable that's preset to what? 729. If I mod 10 into 729, I will have 9 leftovers, because what happens is 10 goes into 729 172 times, right? The 9 wasn't there. There's 9 left over, so it's the remainder. If I do the floor division, it gives me 172 and the 9's ignored. And these are all like fairly basic little examples, but something you might want to try to wrap your head around. All right, this is a great logical stopping point, because you see that the next section we're going into is called calling functions, and this tells me exactly what homework I should assign to you guys. So this is what's going to happen. Chapter 2 is going to stretch another week, so we're going to cover the second half of Chapter 2 next week. We'll start out the same way, so I'm going to give you some homework problems that match up with the lecture I just gave you for next week. We'll do those in class, and then we'll finish up the chapter, and you'll have a second set of exercises for Chapter 2. All right, folks, thank you for being patient and everything, and we'll see you all next week. Video ends here.